Good morning, everybody. The panel and the participant. Today, I am going to present my analytical chemistry postgraduate research study on the topic trends in encapsulation capacity of dendrimer with varying covalentity and generation. This is my outline. I am going to going through introduction, application, objectives, methodology, and we have 5 steps there, and discussion and conclusion and reference. This is as an introduction. I can say the dendrimer, the word is made of two different Greek words, dendron means tree and mero means part. Dendrimer are tree-like heavily branched molecule with a well-defined and a 3D structure. In a dendrimer, we can identify three main component: core, generation, and the co-coordination. Generation means how many homogeneous layers has occurred from core to outer layer, and co-coordination means number of branches that attach to core molecule. Also, you can see the surface molecules and internal core here. As an application of to a dendrimer, I can say dendrimer can be used to deliver drug molecules to a specific location using targeted moiety. For example, we can say a cancer cell. We can deliver drugs to a cancer cell. Drug can be attached to a dendrimer as conjugated drug, encapsulated drug, and absorbed drug. Our objective is to find the structural and properties relationship of dendrimer with varying co-coordination and the generation. There was no any previous work on co-coordination, and we use computational method because we can create a very pure system, and also we can observe experiment data which cannot be performed in real experiment and real environment, and also we can change the structure of dendrimer as we desire. We use molecular dynamics for our research to apply the motion of atoms. We applied Newton laws to atoms, and also we use computer software, visual molecular dynamics for visualization, and lamps for applying the to set up the environment. And also we use cross-grain models. Cross-grain models means it is a simplification of all atomic representation to a simple several bead. For example, you can see the atomic protein has many beads, and it has simplification to a simple several bead. We create our dendrimer, and in step 1 we create our dendrimer as hydrophilic outer core and hydrophobic inner core. We use MH bead, that means CH2. This MH and CH for coding purposes and naming purposes. MH bead as CH2, and it grow to another CH2, and branching will start from BH bead. And it will again continue to another ester group, and finally outside layer will be ether and hydroxyl group for making the dendrimer outlays more hydrophilic. We create different co-coordination. That mean how many branches occurred from core, and you can see C1 mean one branches begin from the middle molecule, and C2 likewise, C2, C3, C4, and C5 and C6. And also we create different generation G3 to G5. G3 mean there are 3 homogeneous layers in this dendrimer from core to outside, and G4 mean there are 4 homogeneous layers. G5 mean there are 5 homogeneous layers. So far we created C1 to C6 dendrimer and G3 to G5 dendrimer, and also our next step was to equilibrate those dendrimer in different system, water phenol and water phenol system. to determine the drug loading capacity finally. And also we try to observe the dendrimer behavior using different methods, be it distribution calculation and volume fraction data and radius of gyration data. This is our condition we used in the simulation. We use temperature 300 and pressure at 1 atm. We use temperature and pressure constant at um, constant using North Hoover algorithm, and also we use RESPA integrator to determine the trajectory. This is how we did incubate those dendrimer, and we kept dendrimer inside a water box and let it incubate under those conditions 300 Kelvin and 1 atm. Uh, uh, and this is the our simulation. We observe our Dendrimer change its shapes under 20 nanosecond and 1000, which that means 1000 frame. Um, 50 frames represent 1 nanosecond, and you can observe Dendrimer change its shapes over the time. And also we create Dendrimers in phenol inside the phenol box, and this is our observation. And as same as in water, in phenol, Dendrimer try to change its shapes over the 20 nanosecond. Most importantly, this is our setup for the determine how much drug can be captured inside this dendrimer molecule. We use phenol as our drug molecule because phenol has fast diffusion rate and intermediate hydrophobicity similar to many drug molecule. We captured those dendrimer with equilibrate drug molecule and kept inside this water box, and this water box was also saturated by bottom phenol layer. We kept this bottom phenol layer to avoid bottom phenol layer, and we keep this bottom phenol layer to avoid droplet formation inside the water box. And also we let it incubate over the same condition and same time. This is what we observe. You can see here in red the initial captured drug molecule has come outside dendrimer, and also um, outside drug molecule has captured inside the dendrimer molecule. This is our result and discussion. We try to understand dendrimer behavior using radius of gyration value and volume fraction data. Radius of gyration mean how this dendrimer has spread, how the dendrimer mass is spread from core to outside of the dendrimer. And also void volume fraction mean how much empty volume is available when it is in a different solution. This is our radius of gyration data, and we plot it radius of gyration versus different dendrimer co-coordination. We observe radius of gyration is increased when co-coordination is increased because simply the dendrimer increase its mass different over increasing the co-coordination, and it try to dense in outer try to dense its mass out in outside of the uh, near outer layer. And also radius of gyration value, and also we try to get plot the radius of gyration value over different generation. And when generation is increasing, the mass is increasing also, and you can observe radius of gyration value is increased as well. The void volume fraction, we try to observe the void volume fraction. The void volume fraction mean uh, how much empty space over collecting 1000 probe points. We plot void volume fraction versus distance from core to um, outside of the dendrimer. You can observe here in red the void volume fraction is very negligible. And also we try to observe resolve hydrophobic and hydrophilic beach distributions, what we and also loading capacity uh, data in hydrophilic and hydrophobic beat distribution. What we try to do is we plot the probability curve and we compare different system to understand how these dendrimer behave in different system, and also in loading capacity of dendrimer, what we try to do is uh, to to get the to get we got the loading capacity data and fit into a equation and compare those to find out which uh, generation is the highest, which dendrimer has the highest ability to capture the most molecule. This is our behavior, this is our dendrimer behavior in water. What we try to do, what we did here is we plot a normalized probability curves versus distance from core bit to outside of the dendrimer molecule. Here we plot over different generation and different co-coordination, and you can see in dash line it is hydrophilic beads, and in hydrophobic beads are in solid line. You can see here the hydrophilic beads are more distant from core, and while hydrophobic beads are stay close to the core. Uh, and also we try to plot this in phenol system, normalize probability versus distance from core. uh, we can observe that the same pattern like in water. Hydrophilic beads are more distant from core, and hydrophobic beads are stay close to the core. This is where we compare the dendrine behavior in different system. We plot our normalized probability value versus distance in different system. You can see here is in water dendrimer has more condensed, and phenol has in phenol it has stretched little bit, and also in water phenol system dendrimer has more stretch. uh, we can say that because dendrimer behave according to the solvent flavorability, and water try to scratch it outside layer, and the captured drug molecule inside the dendrimer try to repel its inner core, and it try to more expand inside and uh, stretch from the outside. And we plot the loading capacity of dendrimer. This is the most important fact we try to find. Loading capacity mean how much drug can be captured inside this drug molecule over its as a drug molecule as a ratio of mass of the dendrimer as a percentage. We try to fit these data into this equation, uh, and the MR mean here is a loading capacity data, and MI mean initial excess loading capacity. ME mean interrupted mass of phenol at time t. P minus P mean decaying constant, and T dash mean these are time parameters. This is our loading capacity over different co-coordination. What we did here is we plot loading capacity values versus time in for different co-coordination. You can see here in red this C5 dendrimer has the highest ability to capture the molecule, and that means highest loading capacity. This is our predicted value over for 100 nanosecond. You can observe that GC5 in red has the highest loading capacity. And also we try to fit those data into this equation, and we observe 56 percentage for C5 dendrimer, and these data were fit around 0.98 R squared value. And also we try to fit this loading capacity data over different different generation, and what we observe is G5 has the highest ability to capture the molecule. This is our predicted graph, and this is our predicted graph for the different generation, and this is and we found G5 has the highest ability to capture the molecule at 87 percentage. Those data was fit around 0.98 R square value. This is our predicted graph for the different generation. In the conclusion, I can say the maximum weight percentage is when we change the different co-coordination while keep the generation is constant. What we observe is C5 has the highest ability to capture the molecule, and C1 is the lowest, and also C C1 has no ability to capture the molecule. C2 was the lowest, and G3, C4, and C6 was in between C2 and C5. With the increasing of generation of the Dendrimer series, and also we change the change generation when keeping the co-coordination constant. We observe G5 has the highest ability to capture the molecule, while G3 is the lowest and G4 was in between G3 and G5. These are my reference.